Today we're going to cover measures of central tendency. These are quick ways to find the middle or typical value in a set of data. The three you need to know are mean, median, and mode. The mean is the same as the average. Add up all the numbers, then divide by how many there are. But remember, the mean can be pulled up or down if you've got extreme values. Let's say 5 workers complete a safety inspection in minutes 10, 12, 12, 14, and 1 worker at 40. Add them up, that's 88. Divide by 5, the average is 17.6 minutes. But look, most workers were much faster. That 140 drags the average up. The median is the middle value when the numbers are lined up in order. It's not thrown off by extremes. Using the same times 10, 12, 12, and 14, and 40 in order, the middle number is 12. That's the median. It tells us more about the typical worker than the mean did. The mode is the number that shows up most often, good for spotting the most common result. In our inspection times, 12 shows up twice. That makes 12 the mode, the most common time. Here's a practice question. In a plant, 19 workers lifted 15 pounds, and 1 worker lifted 250 pounds. Which measure of central tendency best describes the typical lifting load? The answer is the median, because it ignores the one extreme. So remember, mean is the average, median is the middle, mode is the most common. For safety data with outliers, the median often tells the truer story. Measures of dispersion describe how spread out data is not just the center, but how far values stretch. Think of it as safety incidents close together in numbers or scattered all over. The range is the simplest measure, the difference between the largest and the smallest values. Practice demonstration. Suppose PPE violations ranged from 2 in one week to 10 in another. The range is 8. That shows quite a spread. Standard deviation shows how much data varies from the average. Low standard deviation, most values are near the mean. High standard deviation, the values are spread out. If a crew's ladder inspections average 10 per week with a deviation of 1, they're consistent. If deviation is 6, some weeks are 2, others 18, a lot less predictable. Variance is simply the square of the standard deviation. It's less intuitive, but it's used in calculations to show variability. You won't be asked to calculate variance often, but know that if the variance is high, incidents are all over the place. Population is the entire group that you care about. A parameter is a fact or measure from that whole group. For example, the true average number of injuries at all of a company's sites is a parameter. A sample is just part of the population. A statistic is a measure from that sample. If we only track 3 sites instead of all, that's a sample, and the average from those is a statistic. Inferential statistics means using a sample to make predictions about the larger population. Safety pros do this when they use a small crew's near-miss data to predict trends company-wide. An event is just a specific outcome, like a worker slips or a machine malfunctions. Each event is one possible result. Probability measures how likely an event is. It's always between 0 and 1, or 0% to 100%. If 2 of 10 forklifts fail inspection, probability of picking a failing forklift is 2 over 10, or 20%. A probability measure is the rule we use to assign probabilities. It makes sure all outcomes add up to 1 or 100%. The probability of an event is simply the chance that event will occur. If 8 of 10 workers wear helmets, probability of randomly checking one with a helmet is 8 over 10, or 80%. Not all outcomes are equally likely. Likelihood compares outcomes. For instance, if slips happen 12 times a month but falls only 2, slips are 6 times more likely. On the OHST exam, expect conceptual questions, not heavy math. For example, which measure of dispersion is least affected by outliers? Your answer is the standard deviation and variance, not the range. When we talk about determining the outcome in a simple sample space, the idea is just to list every possible result. Think of it like drawing a tree or making a quick chart. For example, if you have 3 objects, you can map out all the ways they can be arranged. Once you see the list, it's easy to notice there are 6 possible orders. But not every problem is that neat. In a less straightforward sample space, the choices multiply fast. That's where we use tools like the multiplication principle, permutations, and combinations. Multiplication is when we figure out the total possibilities by multiplying the options together. Permutations are about order. If the sequence matters, every arrangement counts as different combinations are about groups. If order doesn't matter, we only care about the set itself. So the simple problems, write it out. The more complex problems, use the formulas to keep from drowning in possibilities. Either way, the goal is the same, make sense of the outcomes so we can work with them. Sometimes we need to figure out how many different outcomes are possible. A permutation counts the number of ways things can be arranged when order matters. For example, lining up 3 books on a shelf. Switching their order makes a new outcome. A combination counts the number of ways to choose things when order doesn't matter. For example, picking 3 fruits from a basket, it doesn't matter if you grab the apple first or last, it's the same set. So permutation equals arrangement. Order matters. Combination equals selection. Order doesn't matter. Both are tools to calculate possible outcomes depending on whether order makes a difference. Let's look at this on the job site. If I need to schedule 3 workers into 3 specific shifts, the order matters. Who works morning? Who works evening? Who works night? That's a permutation problem, because changing their order changes the outcome. But if I'm just choosing 3 workers out of 10 to send for safety training, it doesn't matter who's listed first or last. That's a combination problem, because order doesn't matter, only the group itself. When we want to know the probability of either one event or another event happening, we add their probabilities. For example, if the chance of rain is 30% and the chance of strong winds is 20%, then the chance of rain or wind is about 50%, as long as the 2 don't overlap. So the addition rule is about this or that. When we want to know the probability of 2 events happening together, we multiply their probabilities. For example, if the chance of rain is 30% and the chance of your truck starting is 90%, then the chance of rain and the truck starting is 0.30 times 0.90 is 0.27 or 27%. So the multiplication rule is about this and that. Events are mutually exclusive if they cannot happen at the same time. For example, rolling a die and getting a 2 or a 5. You can't roll both on one throw. So those outcomes are mutually exclusive. 2 events are independent if the result of one does not affect the other. For example, flipping a coin and rolling a die. The coin doesn't change the die's outcome. 2 events are dependent If the result of one does affect the other, for example, drawing one card from a deck and then another without replacing the first, what's left in the deck changes the probability of the second draw. Conditional probability is the chance that one event happens given that another event has already happened. It answers questions like, what's the probability of event A if we already know event B occurred? We write it as P of A given B. That's written with a vertical bar, P parentheses A vertical bar B, close your parentheses. It means the probability of A happening if B has already happened. Suppose 30% of all workers wear safety glasses. But if we already know a worker is in the welding shop, the chance goes up to 80%. That's conditional probability. The condition, being in the welding shop, changes the probability. Sometimes we want the chance that at least one event happens, meaning one or more. Instead of adding up all the ways it could happen, we use a shortcut. Find the chance that none happen and subtract from 1. The formula is the probability of at least one equals 1 minus the probability of none. We write it like this: P, open parentheses, at least one, close parentheses, equals 1 minus P, parentheses, none, close parentheses. Suppose the chance of rain on a given day is 20%. What's the chance it rains at least once in the next 3 days? First, find the chance of no rain in all 3 days. 0.80 times 0.80 times 0.80 equals 0.512, 51.2%. Then subtract from 1. 1 minus 0.512 equals 0.488. So there's about a 49% chance it rains at least once in 3 days. Empirical probability is based on actual data or experiments, not theory. We look at how often something happened in the past, then divide by the total number of trials. The empirical formula is empirical probability equals number of times event happens divided by total number of trials. Suppose we flipped a coin 100 times. If it landed on heads 47 times, then the empirical probability of heads is 47 divided by 100, which is 0.47 or 47%. It's based on real results, not the theoretical 50%. Objective probability is based on facts, data, or known formulas. It's measurable and repeatable. For example, the probability of rolling a 3 on a fair 6-sided die is 1 out of 6, or about 16.7%. That's an objective fact. Subjective probability is based on personal judgment, experience, or opinion, not exact data. Different people might give different answers. For example, a worker might say there's a 70% chance a project finishes early. That's not from math, it's from personal belief. A confidence interval gives us a range of values where we believe the true answer lies. It's not just one number, it's an estimate with some margin of error. For example, instead of saying the average score is exactly 75, we might say it's between 72 and 78 with a 95% confidence. A confidence interval tells us how sure we are about our estimate. The wider the interval, the less precise the estimate. The narrower the interval, the more precise. So confidence intervals show both the estimate and our certainty. Most data in the real world has a pattern. It clusters around the average. The 68, 95, 99.7 rule is a quick way to describe that pattern. It says in a normal bell-shaped curve, about 68% of the data falls within one standard deviation of the mean. About 95% falls within 2 standard deviations, and almost all 97.7% falls within 3 standard deviations. This rule helps us see what's unusual and what's usual. If a test score is 2 standard deviations above average, that means it's higher than about 95% of all scores. Pretty rare. The 68, 95, 99.7 rule turns a confusing curve into a simple, powerful way to judge how extreme or ordinary a number is. A z-score tells us how far a number is from the mean, measured in standard deviations. A z-score of 0 means the value is actually average. Positive z-scores are above average, and negative z-scores are below average. Z-scores let us compare values across different sets of data. For example, a test score of 85 in math and 92 in reading might not mean much until we see their z-scores. If math has a z-score of positive 2, that means it's way above average. If reading has a z-score of 0, that means it's just average. Z-scores turn raw numbers into a clear picture of how unusual or ordinary they really are. You've just seen how statistics can help us make sense of numbers, whether it's finding the average, spotting what's typical, or judging what's unusual. These tools let us turn data into clear decisions. In the next lesson, we'll switch gears from numbers to the human body, anatomy and physiology. It will show us the systems at work inside every worker, because understanding people is just as important as understanding the data about them.